Yeah, okay, so what we plan to do is to continue with the discussion of um, the linear models, and we're going to go from estimation to inference, which is, um, I mean, will become clear what we mean by that. But so far, we had point estimates of the parameters of interest, like beta hat, mu hat, and s squared. And under the normality assumption, the D2 assumption, we have a sampling distribution for beta hat, which turns out to be normal. And we also have proved this result about s squared. If you recall what s squared was, it was the sum of squares of the error, or rather residual vector, divided by sigma squared. And so, sorry, divided by n minus p plus 1. And this was our unbiased estimator of the variance in the model. And in particular, we showed that this norm divided by sigma squared is chi squared n minus p minus 1. And if you rearrange, you get that this result holds. So this quantity is basically norm of e squared divided by sigma squared. And so it's going to be chi squared. And the other key fact that we showed is that these two quantities, beta hat and s squared, and as a consequence, this quantity are going to be independent under the E2 assumption, okay? So anyone remembers how this worked out? Why we did get the independence? What was the key fact that led to this independence? Yes.
Is it because of what spaces that E and theta are?
D space?
This is, yes, so E is in the index.
Oh.
Yeah.
Right, okay, so that was the geometric, the geometric idea or the properties of least squares would give you that they're orthogonal as vectors. But then it would imply something statistically, which then led to this. So what was that? What did we conclude? From that geometric fact, we got a statistical fact. You remember? Yes. S squared is unbiased, yes, but I'm talking about the independence. So what kind of we did a calculation that led to a conclusion here. Yes.
Under E2, we had beta hat ER multivariate.
Okay, great. Yeah, so this was the first fact. So under that assumption, E2, these are normally distributed or multivariate normal. And then the next step is we also did a calculation.
We then showed they were
Uncorrelated, yeah. So we did calculate the basically covariance of this vector, covariance matrix of this vector, and in particular, then there was this block partitioning, and then there's this cross covariance matrix, basically beta hat and E, and this turned out to be 0. So this showed that they're uncorrelated. So this would be true even under that E1 assumption, but under E2, this would imply independence, okay? So beta hat and E would be independent. And then why beta hat and let's say S squared are independent? That's another like little argument. You see everyone is on the same page. So S squared is not exactly the E vector. It's a function of E. Actually, a good point. It's not a linear. It's not a linear function. It happens to be a nonlinear function of E. But that's still fine because we're talking about independence. So any function of an independent vector is going to be like 2 and 2. If you have two independent vectors, any function of one is going to be independent of the other. It doesn't have to be linear. So that's a key fact that we use. So, and then this whole thing would be another function of the E vector, nonlinear function. And then this is clearly a linear function of beta hat. It's just identity function. And so they're going to be independent. Okay, so the independence buys us this strong property that we can then use to argue that so just uncorrelated wouldn't be enough. For example, if you just had that the E and beta hat are uncorrelated, then we couldn't say that this guy is uncorrelated from this necessarily, because this is not a linear function. So it's not like uncorrelated, and this is not preserved under nonlinear transformation. But independence kind of is preserved. Okay, so these are basically a summary of these results. So what we want to do is now to use this to do some statistics, like a little bit more advanced statistics. So what are these useful for? We want to draw conclusions, okay, about the underlying world or underlying model or underlying the truth, let's say. So in order to do that, I'm gonna basically, let me just briefly mention what it is. So we're going to do a statistical inference in the sense that we're going to use the sampling distribution to make probabilistic statements about the unknown true parameters, okay? Or make decisions about their values if you want. And the two basic tasks are, let's say for a single beta j, we're going to focus on inferring something about beta j, would be to build a confidence interval and do hypothesis tests. So what is the confidence interval basically allows you to quantify uncertainty about beta j, and the hypothesis test allows you to make decisions about beta j. For example, answer questions of this form. Does predictive j have any effect on the response? So if you recall, for example, let's say if you have a very simple linear regression, the equation is like this at the population level. If I want to know if the covariate x has any influence on y, I can test whether beta 1 is 0 or not. If it's 0, then it drops out of the model, and then x does not have any influence on y. If, however, beta 1 is non-zero, then x exerts some sort of influence or some effect on y. And so testing whether beta 1 is 0 versus beta 1 non-zero would be an example of the test to do. For confidence intervals, do people know what confidence intervals are? How many people know confidence? Okay. How many people know, like, have heard of hypothesis testing? Okay. So we'll see how well we know this. So I want to emphasize the probabilistic kind of meaning a little bit more today, because then we're gonna go into details of driving these. I just want to make sure everyone understands fully what these are, okay? And then you're gonna help me try to define these. So far, so good. So today is gonna be like a little bit of background and sort of foundations of these concepts, plus doing inference for beta j. Then you're gonna extend to regression functions, the regression function and prediction on Thursday. Okay, so far so good. Okay, so this is where I want to spend a little bit of time remind you what we have in a probability model or an abstract probability model. So our model is this linear model, and we assume that basically this noise is random. Once we head it into the statistical kind of land, we assume that this is a random vector. And so it implies that y is a random vector. Which in principle means that y is not really a single numerical vector anymore. It represents an ensemble of possible values and that lives in like an abstract probability space, or that there's an underlying probability space. So it's not a single numerical vector. That's what I want to emphasize a little bit. As a random quantity, it represents an ensemble of possibilities. Okay, every time you repeat the experiment, you get a different y. Okay, and this kind of extends to all the parameters that we drive, or all the things that depend on y. For example, beta hat would also represent an ensemble of values. Okay, basically each value would be a vector, a realization of beta hat. So beta hat is a random vector on this ensemble. In practice, we observe often one realization of this in practice, but the statistical properties like covariance of beta, covariance matrix of beta hat that we derive, or this statement about the distribution is another such quantity. These are about the ensemble values. They're not about a single realization. Okay, that's what I want to enforce a little bit. And the easiest way to see it is if you use the frequentist interpretation of probability. How can we observe this ensemble in practice? In real applications, usually you don't, but in simulations you can. So you can, for example, this is the setup that I have here. So you can try to generate from a simple linear regression. I guess the microphone ran out of battery. Give me a sec, I can try to. These are all dead batteries, but we can get as much as possible for a few minutes out of them. Okay, so let's say I have this regression line. So these are in Rn. So this is in Rn. Sorry, not the regression line. This is like a simple linear regression. I'm gonna take n to be 20. Beta 1 is going to be 2. I guess beta 0 is like intercept is 0, beta 1 is 2. So that's our true model. Then I'm going to generate, and then x would be a sequence of scalar values that we draw, I think between 0 and 4, something like that. So I draw from this model once, I get a realization of y, and then I can fit and then I have an x as well. So you get the y vector. And then you have the x vector, which is the columns of all ones, and then the vector x here, which is representing that single covariate. And you regress basically y on x, let's say, and you get beta hat. And once you get the beta hat, you get the fitted regression line, which is going to be y is equal to beta hat 0 plus beta hat 1. Let's say x, this is really a line, let's say. Here, let's say these are vectors. Here, this is just a scalar. This just represents a line. If you want, you can write it as maybe write it as mu of x. So this is a scalar. And I'm going to plot this function. It's like a linear function. And I'm going to plot that function. So that red line here, if you see here, this is the true regression line. That would be, if you want the true, you can say mu star, the true regression line would be basically 0 plus 2x. So that's this line that I plotted. And then I get this mu hat, which is our fitted regression line. That would be one of those blue lines. And then I repeat the whole experiment again. I draw another 20 sample, but basically vector, and then fit another beta hat, I get a different line. I get another one of those blue lines. And here I've repeated 50 times. So we draw 50 realizations, and I've drawn that on that picture, okay? So that's the ensemble kind of view, okay? So the beta hat kind of is different in each case, and each one gives me a different regression line. So you get an ensemble of regression lines as well. And you notice some interesting features. For example, it's like kind of the range is wider there and basically narrower there. And this feature we can actually prove, as we'll see next week. The tools that we develop, we can actually argue that it should be like this. But you can see like the variation that you get is a feature of the ensemble, not a single realization. And then the statistical properties are about that ensemble. Okay, so statisticians don't care about a single one of these lines, they care about this ensemble as a whole. And the same goes for beta hat. In each case, you get one realization of beta hat, but overall, I get a bunch, and then here I'm plotting a histogram on this side. So in each experiment, I get one of these values, but as a whole, I get, let's say 50. Here, actually, I'm drawing 5,000 realizations because 50 would be small too. So that's a nice histogram. So I repeated the experiment 5,000 times, and that's what the histogram of the values look like. And you can fit a very nice Gaussian to it. And so it matches our theory. So we are saying, for example, that this is a Gaussian. What it means is that the distribution or the histogram of these beta hats that you get would look like a Gaussian density. Okay, and then you can actually exactly calculate. We know that it has to be centered on the true value of beta, which is 2 in this case, and you can see that that's exactly the case. So it's centered around 2. And then there's going to be a variance to it depending on the sigma squared. I think sigma squared, I actually set in the simulations, you can also set it. It's probably set at equal to 1. So sigma squared is 1. And then depending on the actual, I think if we fix here, the idea is that we fix the x values. And so that x transpose x inverse is going to be a 2 by 2 matrix. And from that, you can read, given the sigma squared, exactly what the variance of this normal would be. And then you can plot that red line, which is the theoretical sampling distribution. That's the distribution of the beta hat under our model, and it matches what you observe. Okay. Does this kind of make sense? So statisticians don't care about a single realization, a single like value of beta hat. They care about this ensemble. They care about the distribution. They care about the variation. Okay. They care about the variance and so on. That's kind of the statistical view. Questions about this? Okay, makes sense so far? So like in fact, what we are working with is like a not like 50 realization or 5,000 realization. We are working with like infinitely many. Okay, so these live in the case like in the abstract space where you have infinitely many realizations. So this distribution is for the case that you're looking at the ensemble of infinitely many realizations that can be generated from the model. And then in practice, you can approximate it by many realizations, not infinitely many. Okay, I think that's good enough. I mean, have this picture in mind. Every other thing that we do has this dual characterization. You work with, in the statistical domain, you work with this ensemble. In practice, you just observe usually a single value. And you have to be able to distinguish between these two to not get confused, okay? So when we make statements, we are often making statements about this ensemble, not about that particular value that you observe in practice. Okay, so now let's define the confidence intervals. Let's see if you can help me define it. So what is a confidence interval now? If I want to, for example, build a confidence interval for beta j, what do I mean by that? Yeah.
You need standard error.
No, just before we get to what we need, what is the definition? What is it exactly?
It's basically possible range of values that are
A possible range of values that the point estimate can take. So by definition, point estimate is just a point. So we need to refine that statement. It's not a point estimate. So it's a different kind of estimator if you want. So if you want to be a little more precise, anyone else can be maybe more precise. I'm gonna rotate through these. Yes.
Is it like a fixed parameter?
So the fixed parameter is the true parameter that we are trying to estimate. So the confidence interval is sort of like an estimator. Okay, it has some relation to the true parameter, which is the fixed parameter. But I want you to maybe help me understand exactly what is the definition of it. Anyone? For example, I say I have a 95% confidence interval for beta 1. What does this mean? Yes.
The concept of that is that you have a range of values that you're 95% confident that beta 1 is 2 parameter, or excuse me, false in that.
Okay, good. We have a range of values that we are 95% confident that beta 1 lies in that. So what does that mean, like 95% confident? What exactly do we mean? Yes.
So if your example 100 times, then 95 time, then 95 adjustments you're confident with the true parameter value will lie.
Okay, this is good. Yeah. So what we mean is that's like a frequentist interpretation of the probability. So when you say 95% confident, what we really mean is the probability. So the actual statement would be something like this. I was hoping something like this. So the 1 minus alpha, let's say alpha is 0.05% confidence interval for beta j is a random interval. So it's one of those kind of ensemble quantities. Rather than a single number, it's just like a random quantity. So it's an interval whose endpoints would be random numbers. Okay, so it's a random interval rather than a random vector or random number, such that the probability that beta j belongs to this interval is 1 minus alpha. Okay, and so this is the precise mathematical statement, but in practice, when you try to interpret this probability, oftentimes if you're a frequentist, you interpret it as frequency of observation. So you repeat the experiment as we did many times, let's say 100 times, and approximately 95 times out of the 100. So in each one of those realizations, this take like a deterministic value will give you a particular interval, and out of those 100 intervals, like about 95 of them would contain the true parameter. Okay, so here is an example I did. So we are doing like 60 realizations, and here's like a 90% confidence interval. And you can see in each realization you get a different interval. Beta 1 is still 2, but except those red intervals, everything else contains the true parameter. So it intersects with that line. These red ones are kind of missing that, okay? So this is basically the frequentist interpretation. If you want to be mathematical, the definition is there. You don't have to be frequentist. It's just lives in the probability space. So it's a random interval that contains the truth, or in other words, the truth belongs to it with probability 1 minus alpha. But if you want to interpret it in practice, usually you take one of the interpretation probability is frequentist interpretation, which means that if I repeat the experiment many times, the fraction of cases in which this statement is true, that would be approximately the probability, that has to be 95.95, okay? Does this make sense? So what it means is that in practice you observe one of these. It could be that you observe this, and it could be that you observe that, okay? From a single realization, you can't kind of tell anything, okay? And statisticians really don't care about that particular instance. Okay, whether the true parameter belongs to the interval or not, we can't say anything about it based on a single realization. What we can say is if you have many of those, then on average, 95% would contain. Okay, this is very important to understand. Right. So when you do like a single experiment, you construct confidence interval, it turns out to be like a deterministic interval, and you see, for example, that 0 is in there, or like if you're testing whether beta 1 is 2, 2 is in there. That's it. So, I mean, that's the conclusion, but we can't say really that much beyond that what we have here. Okay, if you repeated the experiment many times, you can be sure that 95%. It could be one of those cases, but it could be one of these other cases where it doesn't contain. So you're just hoping that, okay, maybe we're in a good case. If many people repeat the experiments, then it's going to be a little bit more sure. Okay. That's why single experiments are often not necessarily liked by a statistician. So if you have a scientific fact that someone did the experiment once and have a result, that may not be as reliable as like many people try to replicate it, and across many people, like majority of people found out like the conclusion. Then you can be a little bit more confident. Okay. So far, so good. Okay, so that's the meaning of the confidence interval. What is a hypothesis testing problem? It's kind of similar, but here rather than building like an interval, we're gonna decide whether, for example, that particular parameter takes a certain value or not. So, for example, we are testing. So we have two hypotheses: hypothesis 1 and 2, or sorry, 0 and 1. 0 would be null, 1 would be the alternative. Under null, for example, we assume that beta j takes a certain value, beta star j, which is often the default. So let's say it could be 0. Most often people want to test whether beta j is 0 or not, but it could be any other number. And then under h1, for example, we can test whether beta j is not equal to beta star j. Okay, whether it's equal or not. So you're deciding between these two complementary hypotheses. I hope you have seen kind of the idea. The fact is, this is actually a composite hypothesis. A simple hypothesis would be, for example, I test whether beta j is beta star j or maybe gamma star j. I have two certain values. I decide between the two. This is called a simple hypothesis. The H naught is also simple here. This is a composite, which is it contains multiple possible values of beta j. It's not a specific value. And a feature, okay, so in this problem, what you do is usually you define a decision rule, okay? A test or a decision rule based on y, which is basically a function that maps y to a binary decision. They might show it as delta y would be, let's say, 1 if we often construct a test statistic, which is, let's say, represented as ty here. And often, like, people do a two-sided test. This is not, doesn't have to be like this, but most of our tests are like this. So you construct a test statistic, which is just a function of y, a numerical function of y. And then you reject, for example, based on the extreme values of it. If it's bigger than, the absolute value is bigger than the threshold, then you'd say that the alternative is, we decide for the alternative. If it's less than that threshold, we decide for the null. So this binary decision is your decision rule, and it's captured in that kind of, sometimes we write it as an indicator. So delta y is really the indicator that ty is bigger than u. So this is saying if that ty, the absolute value is bigger than u, then it's 1, otherwise it's 0. So it doesn't have to be, the decision rule doesn't have to be, for example, exactly like this. You could have a statistic and you reject for small values of it, as we'll see. Okay, or we could have a complicated decisions set. So you define a set. If y belongs to that set, you decide for y. So say for 1 for the alternative. If it's in the complement, you decide for. So it doesn't have to look like this, but this is very common. So you build a statistic such that if it's extreme, then you would reject. So far, so good. So the issue here is, which is often maybe not obvious when people first encounter hypothesis testing or statistical models, is that we have at least two sets of realities. So when you have the model, you have y is x beta plus epsilon. Let's say we are in this simple case where we are testing whether, for example, we test whether beta j is equal to, let me do it actually simpler. So this is really, let's say y is beta 0 plus beta 1 x plus epsilon. So I'm just gonna test whether beta 1 is 0 versus beta 1 is 1. Okay, this is the simple hypothesis. I really have two possible models, one in which this is 0 and one in which this is 1. So we have two different models. So y is beta plus x plus epsilon. Okay, and so the distribution of y would change depending on which model we are under. And so the distribution of ty would change, for example, whatever statistic we have under the two models. And so we end up getting two different probabilities for rejecting the null. Okay, and people would represent this with pi naught or pi 0 and pi 1. So when I say pi 0, it means the probability model under the H naught assumption, and here will be under H1 assumption. And rejection here would be just the probability that the decision rule is 1. So rejecting the null means I decide for 1, and this would be really what we call the type 1 error. So under the null, you don't want to reject the null. So this would be an error. And the probability that that happens would be called type 1. This is one of the bad cases that could happen. Sorry, let me try to extend. Let's see how long this one lasts. So this is one of the types of probability of error. And the other one is when you're under the alternative, the probability that you don't reject, this is going to be the probability under 1 that delta y is 0. So this is also bad. So if you're under the null and you decide for 0, then this is not good. And ideally, you want to minimize both, but they're kind of in conflict. And if you've seen 100b, there are different ways of dealing with the fact that you can't drive them both to 0 at the same time. I can always drive one of them to 0. For example, I can always decide for 1 and just throw away the information, always decide 1. And then, for example, type 1 would be always 1. Type 2 would be, type 2 would be 0. So if delta y is always 1, my type 1 errors would be 1, the other would be 0, or vice versa. The interesting is that if I can drive them both down, not one is 0, the other is 1, or vice versa. And in this course, we are going to focus on this type 1. We are going to make sure that it's below a certain level, like 0.05. We don't worry too much about this, unless maybe exercises. If you have a good test, you expect that, okay, if I control type 1, and I have a good test, maybe type 2 is also going to be small. In 100B or like more advanced courses, you try to find the optimal test. And that given a certain type 1 error, you have a budget of type 1, like you want to make it less than 0.05, how can I design a test such that you minimize the type 2 as well? Okay. But focusing on type 1, we're going to try to minimize, try to enforce this constraint that probability of rejection under the null is less than alpha, less than or equal to alpha, and this is called the significance level of the test. A test that we often push it to be actually equal to alpha, because the larger it gets, the easier it is to drive the other type of error down. So if you're given this budget, you try to use as much of it as possible. So you end up having a test whose type 1 error is alpha, and that's called the significance level of the test. And that's probably you have heard about it. You say, for example, we reject at level alpha or reject at level 0.05. It means that our type 1 error is below or actually equal to alpha. Okay, that's what we're going to focus on. And we hope that our statistics are good enough that type 2 is also low. And the ones that we do is that kind of either optimal or near optimal. For certain, the optimality depends on the structure of the alternative. It's not an easy question to answer. The type 1 only requires you to know the null. You can kind of set it without knowing what the structure of the alternative is. Type 2, you have to decide like what kind of alternative you want to look at. Is it the simple one? Is it this composite one? Is it like a different shape? So you know that beta 1 is in a kind of awkward shape or something like that. It's more complicated. Okay. So far, so good. Was it fast? Or I assume that you have seen this, but I just want to make sure everyone understand what we're doing. Questions? I'm gonna pause a little bit. Okay, so now I'm gonna do this. If you look at our decision rule here, if our decision rule is like this, then I'm gonna try to, so decision rule is something of this form. We'll figure out the test statistic later, but I'm gonna reject if, let's say the absolute value of ty is bigger than or equal to u, then the type 1 error would be the probability under null that delta y is 1, which is the probability under null that ty is bigger than or equal to u. And if I know the model, the linear, for example, model, and I know the null, for example, the null is beta j, I could calculate this probability, okay? And it's really the inverse CDF, or like 1 minus the CDF, not the inverse, 1 minus the CDF of this random variable. And I'm going to call this GU. So for every value of u, I can calculate this probability. It gives me a function of u, and then I'll set it equal to or less than or equal to alpha. And then this allows me to invert it. Basically, you invert the function. It turns out that, for example, u has to be bigger than or equal to g minus 1 alpha. The reason why the inequality is switched is because g is going to be decreasing. So as you increase u, the probability goes down. And so the decreasing function, so when you apply it, I'll let you like figure it out. Let's say it's like 1 to 1 has a unique inverse. You apply it, it reverses the direction of the inequality. So inverting that function basically allows you to get the range of the threshold, and you push it as low as possible as you want. Pushing it as low as possible would be like minimize type 2, let you argue that for yourself. So our threshold would be like g minus alpha. Okay, so you define that function, you recover that function from the statistical analysis, and you invert it, you get the threshold, sort of. Okay, is that kind of fair? But the thing is, there's a slightly better way, as I'm going to argue. But that's in principle would solve the problem. You have a perfectly specified test, because this is specified now in terms of alpha, and this you can calculate and you can decide. So you just evaluate the test statistic, compare it with this known threshold. If it's bigger than the threshold, you reject. If it's less than threshold, you do not reject the null, and that's it. Okay, so it doesn't tell you anything about the hypothesis being true or not. What it means is that if you repeat this test many times, then only 5% of the time under null, if the null is true, 5% of the time you're going to be wrong. You're going to erroneously reject. That's all that would be guaranteed. Does that make sense? Okay, now I want to do the interesting thing, which is the p-values. I want to make sure that you understand this. If you understood this far, so it's just one little step, and you'd see what a p-value is. So we have this function. I mean, here I'm doing, because the statistics are going to be continuous, it doesn't matter if you do strictly bigger than you or equal to bigger than or equal to you. So we have this function. The interesting thing is that I can apply it to the actual observed. Instead of computing the threshold, I can apply it to the statistic itself, the absolute value of t bar. So I calculate this function, and I evaluate it at that observed value, or the statistic, actually. So this I'm going to call the p-value. And we will see that it's exactly kind of what you have seen before. But in this view, you'd see that p hat is really another random variable. Again, it's a transformation of the original statistic. It's a nonlinear transformation. But because y is random, ty is random, p hat would be random. Okay, so p-value would be a random quantity. The only thing is that it's expressed in the probability scale rather than original scale. So the scale of it is, you can see it's this function describing probability that something is like, the statistic is bigger than a threshold. So this is really, the meaning is of the sense of probability, but it's really not a probability in the sense that it doesn't give you a probability of event. It's really a random variable, but it's just scaled as a probability, or on the scale of probability. That's the only thing. It's like just a transformation that makes this useful. Why it makes it useful? Because then you can prove that no matter what your statistic ty is, under the null, t hat would have a uniform distribution. It's a random variable, it has a distribution, it's going to be always uniform. Okay. You don't need any threshold or anything, so it's just This is going to be always true. You're going to show it in your homework problem. It's like a simple consequence of the probability integral transform. But once you understand this is really another random variable, it has a distribution, both under null and under the alternative. Under null, it would have the uniform distribution. And this allows me to actually redesign the decision rule based on this transform statistic. And the threshold here will be trivial, as we'll see. But this is an example of what you can do to verify this fact. Here I'm having, I think, simple linear regression. Maybe n is 30, certain values of maybe sigma squared is 1, I forgot, beta 1. Beta 0 could be maybe 1 or something. And we have two possible values of beta 1. Beta 1 is either 0, this is the null. And beta 1 is 0.3, this is the alternative. Okay, so under the null, I have calculated, so we're gonna have two distributions, one under the null for every random variable. Under the null, I've done this like maybe, I don't know, many times, 50 times or 100 times. And then plotted the histogram of p hat, and you can see it's perfectly like very close to a uniform, 0 to 1. And under the alternative, you can see it's like shifted towards 0. Okay. And so it's less likely to take larger values, much less likely than under the null. Okay. And this allows us to easily design a test that fact allows us to design a test. So instead of so my original test was in terms of, decision was in terms of Ty. I claim that this is equivalent to now doing a new test in terms of p hat. P hat is a function of y, so I can calculate p hat. So this is going to be just p hat compared to just alpha. And rather than rejecting for large values of the statistic, now we reject for small values of the statistic. So p hat is a statistic. My test statistic is this now. This is the test statistic, new test statistic. And I compare it with alpha. If it's less than alpha, I'm going to reject. So this is just really saying reject if p hat is less than alpha, not reject if p hat is bigger than alpha. Okay, why this would be a test of level alpha? Because under null, if I look at when we reject, this is when we reject. This is p hat less than or equal to alpha. P hat under the null would be uniformly distributed. And the probability that the uniformly distributed random variable takes like on 0, 1 takes values and 0 to alpha is just alpha. Okay, the probability that this is in this interval is the length of the interval divided by 1. Okay, so it's really alpha over 1. But the fact that the p-value would always have a uniform distribution allows me to reject it at level alpha. So I just reject when it's less than or equal to alpha to get a test that rejects at level alpha. Okay, so the threshold calculation is trivial for this. That's the kind of usefulness of the p-value. And for this reason, or originally for other reasons, but for this reason, you report the p-value and you're done. Because someone wants to build a test, they can just compare it with alpha. But the p-hat itself would have more information. You can see how far from alpha you are, which is not the case if you just report this binary. This just removes some of the information in p-hat. But like reporting the p-value would be kind of enough to easily get you a test at the law. You just design the test by saying I'm going to reject as if the p-hat is less than. Now, if you understand all of this, you would understand that just observing. So this p-hat would be this like random quantity. It represents an ensemble of values as many other things. So in practice, you observe a single value. So you might observe p-hat is equal to 0.00049, for example, in your experiment. Just observe the single value. What does it mean? It doesn't mean anything. Okay. It could be under this model, it could happen. So this any value in 0 to 1 could happen under this model, and also under that model. It is less likely under this model, for example, than under that model, but that's all you can say. Okay. It doesn't mean that H1 is true or H1 is true. It just means that if you repeat the experiment many times, collect all these values you see, and let's say reject if this less than, for example, 0.05, you can be sure that 0.05% of that 5% of the time you're going to be wrong. You're going to wrongly reject. That's all it says. Okay. Or you can be kind of a little bit, I don't know, surprised if the null was true, because it would be unlikely that you see it. It would be here, which is contains like this much of mass versus I mean a lot of mass would be here, right, versus here would be like a small like amount of mass. So under this model, under the alternative, that's more likely to be seen than this model. But that's it. Okay. There's no kind of like conclusion about whether H1 is true or H not is true, just from that single number. And if you see p hat 0.9, it could come from this model still, and also from this model, but it's very unlikely to have come from the alternative rather than the null. And that's it. Okay. There's not much else. If you repeat the experiment many times and reject with this rule, then you can be sure that alpha% of the time you're going to be wrong at most under the null. We don't even know what happens on the alternative unless you know this distribution. Does that make sense? I'll let you maybe think a little bit about it. Yes.
It's not like a dumb question, but I was just thinking about the uniform distribution of the null, and it's surprising to me that low p values will still give the same distribution as high p values under the null.
No, that's not a good statement. You can't say low p-values or high p-values. It's just the p-value would be a random quantity, and it will have a distribution under the null. That's it. Okay. And what it means is that observing, like, if that's what you mean, is that observing like an interval, let's say, it's equally probable to observe things in this range and things in this range, if that's what you mean, under the null. Yes. So it's equally probable to see something around 0.8 and something around this, but that's like a fact of life. Right. But the probability is smaller. For example, if you look at this, if you pick it like a tiny interval here, around 0, let's say point 0.1 here. So the probability to observe anything 0 to 0.1 would be 0.1, whereas here would be much higher. Okay, this is going to be non-uniform here. The probability to observe anything here would be much higher than the same length of interval, like here, around here, but here would be equally likely. Maybe that would be surprising, but that's the fact of life, yes. Any other questions? It's good to think about this, and I'm going to post the problem. This one you can easily prove. This is very general. And the advantage is that you get rid of the threshold, you get rid of and kind of normalize everything. So people reporting p-values, they're all reporting on the same scale. Under the null in their problem, it has to have uniform distribution. So there's no surprises. Whereas if I construct a statistic, the statistic would be problem dependent, the threshold would be problem dependent, and the distribution under null would be problem dependent. But once you do this transformation, everything would be kind of expected to be the same. Like p-value would be uniformly distributed under null. Any other question? Yes.
One is, why is that all at 0? If 0, 1 is the right one now. 0, 1, either is the p value, p1 value seems to be different, but you said one under the null. Right?
You mean the range of the value that you had
Why are the p values different? But I see one is under the null and the other is under.
Right, because exactly what we are doing is a hypothesis testing. So we are testing whether beta 1 is equal to 0 versus beta 1 is equal to 0.3. And this would give me two different distributions for if I just had one value, I get one distribution. It's a hypothesis testing, so I get two different distributions. And I mean, you will see what the statistic here would be, but this is going to be the statistic that we'll like construct for this. It's the t statistic that we'll see. I mean, I'm not showing the ty here, but it's designed to it's designed under the null to have you'll see what the statistic is, but once you have the statistic, if you calculate this and evaluate at the value of the statistic, you would get a uniform distribution. Sounds good. Okay, we're out of time. Not out of time, but running out of time. So some people will say a smaller p hat with strong variables against H0. I think what I described is more precise, so you can take it as if you want as whatever it means. Once you understand what is going on, you can interpret it as you want. So there's a duality between the confidence interval and hypothesis testing, and I'm going to be very brief, but you can easily later argue it for yourself. If I build a confidence interval for theta, for parameter theta, at level, let's say 1 minus alpha, I can get a test of level alpha for theta being equal to theta star by just checking whether theta star belongs to that confidence interval or not. So I would reject the null if theta star is outside that interval. That gives me a decision rule or a test that has level alpha for testing H0. So this duality allows me to pass from a confidence interval to a hypothesis testing and actually vice versa. But the other direction, you have to think a little bit more. The practical reading is this. So every value outside the confidence interval is one which we should reject at level alpha if you're testing. Okay, you can build a confidence interval and just get a test for free. Okay, so let's do like actually construct one of these in our problem. So this was abstract, and now I want to apply it to beta j. We need a way to build those test statistics, and the way we do it is that we're going to look for a quantity that involves beta j whose distribution is known and does not involve like beta j or other unknown parameters. These things are called pivot. So a bit more precisely, a pivot is a function of both the observation and the unknown parameter, whose distribution does not depend on the unknown parameter. Okay. It's different from a statistic in that the statistic cannot depend on the unknown parameter itself. A pivot can, however, its distribution cannot. An example from earlier courses, let's say 100B or some other earlier courses, is that when you try to estimate the sample, like the mean of a population, you look at the sample mean, you subtract the mean. The mu here is going to be the unknown parameter, and you divide by the standard error, S over root n. This quantity will have a t distribution n minus 1 degrees of freedom. The distribution is completely known, doesn't involve any unknown parameters, but the statistic itself involves mu. But that's good enough for us because then we can invert the relation and get a confidence interval out of it. That's kind of the strategy. And so why this helps? Because, for example, I can do find the confidence interval by finding gamma such that the probability that the, let's say, absolute value of t is less than or equal to gamma is 1 minus alpha. Because this probability, this is really t, y, and theta less than or equal to gamma. So sometimes like drop the dependence for simplicity. So this probability does not depend on theta, although the statistic is, I'm sorry, the pivot depends on theta. This probably doesn't. So for every gamma, I can calculate what it is, and so I can find gamma such that this is equal 1 minus alpha without knowing the actual parameter. And then we invert kind of this inequality that this gives us. If you set it actually bigger than or equal to 1 minus alpha, gives you an inequality that allows me to bracket theta, as we will see. How does this allow us to build a test? Because let's say under null, if I want to test whether theta is equal to theta star, I set the theta to be theta star. Now this pivot turns into a statistic. This is perfectly known. For example, theta star is 0, so evaluate of y is 0. This is only a function of theta, and its distribution under null is perfectly known. And then I can use it as a test statistic, read off p hat, like p value, so on. Okay, so a pivot would allow us to do both. And you have already kind of potentially seen it. So let's try to build it for beta j. Let's try to find a pivot for beta j. And here, all our previous kind of calculations come into play. So from the previous lecture under E2, we have that beta hat j is normal with mean beta j and a variance which is sigma squared Vj, Vj being the j diagonal element of the x transpose x inverse. So this is like a marginalization of this result that we had. The vector is multivariate normal with mean beta and covariance matrix x transpose x inverse. If you marginalize the j marginal would look like this. And then I get, if I standardize, I can subtract the mean, divide by the standard deviation if you have a normal random variable, and this would be normal, normally distributed under our model, no matter what value beta j takes. Okay, this is true as long as the linear model holds, like y is equal to x beta plus epsilon, and E2 holds. So under these two assumptions, this is true, and this is an example of this affine transformation property. If you want to be stating it in the language of this course, this is an affine transformation of the vector beta hat, or if you want the scalar beta j, or beta hat j, and so it has to have a normal distribution. We can just compute the mean and the variance, and it should be easy for you to do, and just really normal. So this may look like a pivot, except that I don't know sigma. Okay, if I knew sigma, this would be a good pivot because it would only involve beta j, the unknown parameter, and distribution does not depend on the unknown parameter. This is sometimes called the z value. But here we don't know the variance, so we need to work a little bit harder. So what do we do often in this case? Is the answer. How do I deal with the fact that I don't know sigma?
Take the sum.
Yes, basically we have an estimate of sigma, right? So we can just replace it, plug an estimator. So I'm going to replace it with what I use to estimate. So we have s squared, which is an estimate of sigma squared, and so the square root of it would be a natural estimator for sigma. So I'm going to do that. But then so this is good because now this only depends on the unknown parameter beta j. But could potentially be a pivot if I can show that the distribution is not dependent on any unknown parameter. But can I still say that this is normal or not?
SS is not, doesn't take a normal distribution.
Yeah, so this is random, right? And now this is not an affine transformation of beta at j in the sense that it's not a fixed affine transformation. So because this quantity is random, that result that we had doesn't apply because the transformation is random, yes. It's gonna be t, yes. We'll see like shortly. I just want to help you like argue it that it's the distribution is gonna be heavier tail than normal because this can take values close to zero, whereas sigma is like fixed. This can get very close to zero with some probability. So there's a chance that this gets very large, but the probability is going to be small. But the fact that you're dividing by something that can go like be close to zero causes this to have heavier tails. Even if you didn't know that this has a t-distribution, you shouldn't expect it to be normally distributed. You should usually expect it to have heavier tails than normal. Okay, that's kind of the rough idea. And okay, so this thing often is called the, as you probably know, the standard error of beta hat j, which is really just an estimate of the standard deviation. So this would be the standard deviation of beta hat j. Standard error is just an estimate, a plug-in estimate. Okay, so our test statistic is really this. Okay, so beta hat j minus beta j divided by the standard error of beta hat j. And here, there's a bit of algebra that you can do. This was original z. I can write this as z divided by the square root of this u. U here is this rescaled version as s squared. And then divided by n minus p plus 1. So this equality, I'll let you do it. It's just a bit of basic algebra. This as an exercise due to lack of time. But the fact is we have shown that u has a chi-square distribution. That's kind of the first slide that we did. If you rearrange basically the result that we had about the norm of e squared divided by sigma squared, that's exactly what we have here. So if you multiply this by n minus p minus 1, it would be norm of e squared divided by sigma squared, that's chi squared. And if I manage to write it like this, which happens to be the case, you can see this quantity is standard normal. Z has the standard normal. And u is chi squared, the norm has a known distribution. And u and z are independent from the result that we have. So we know the full distribution of this, and it wouldn't depend on any unknown parameter. It happens to be t-distributed, but that doesn't say much, it's just a name. Even if you don't know the name, you can argue that this has a fully known distribution whose basic distribution does not depend on unknown parameters. You can simulate from this distribution by generating a standard normal and independent chi-squared and forming this and repeating the process, plotting the histogram, you get a perfectly good approximation to this without knowing the name, without knowing anything. And the name happens to be the first person who did it, like a student in early 1900. I forgot, it was like very early. Because student has a T, I think they call it T in honor of a student who was his name, the name of the guy who first published it. It's known, you can actually calculate the density and quantiles and everything is kind of known or tabulated or in the software. But for us, it's just the fact that once you have this form, you can easily see that it doesn't depend on any unknown parameters. So we have constructed a pivot. Okay, so now because I have a pivot, which happens to have a t-distribution, nowadays we call it a t-distribution with that many degrees of freedom, which is just the degrees of freedom of this chi-squared that is involved in this definition. Now I can, for example, calculate this probability, the probability that t is less than or equal to gamma under our general model, and I can find gamma such that this is 1 minus alpha. I'm gonna like plot the t-distribution, for example. It's going to be a symmetric distribution around 0 with that many degrees of freedom, which depends on n and p. And then if you look at, it's a symmetric distribution, so it simplifies a little bit. If you look at, for example, the pth quantile, the pth quantile of the distribution would be a value such that the probability that the statistic is below it is p. Okay, so if you look at the pth quantile, it means that this area is the area under below this value is p. Okay, and if I kind of construct it such that the area above basically is, I want the area above to be alpha over 2, because then the area below this TDP would be also alpha over 2 by symmetry. And And so the area in between would then be 1 minus alpha. So the interval between TDP and negative TDP would be would have probably 1 minus alpha. And so if you look at it, because we want this to be alpha over 2, this P has to be 1 minus alpha over 2, because this is the location such that P of the mass is below it, and 1 minus P is above it. And so 1 minus P is alpha over 2, so P has to be 1 minus alpha over 2. So basically, this gamma turns out to be, this calculation you can do it for yourself, would be the 1 minus alpha over 2 quantile of that T distribution. But this is just like kind of renaming it in terms of the quantiles. It doesn't matter, it just matters that you can calculate the gamma. It's just based on the distribution. If this was a little bit fast, you can verify for yourself. Just draw a picture. Are you based on the quantiles or not? It doesn't matter if it's a quantile, just have to figure out the gamma such that this holds and you can figure it out. Okay. What matters is that once I have that gamma, then I have this equation, because the absolute value of T less than or equal to gamma is equivalent to saying T is less than or equal to gamma and bigger than or equal to negative gamma. So that's this equation that I have down here, the two inequalities, and then you can now rearrange. Let me do one of them so you can kind of rearrange. Let's say do the that inequality. So you get beta hat j minus beta j. I multiply by standard error, so I get gamma times the standard error of beta hat j. And then I rearrange, I put the beta j on the other side, and then move the that term gamma times the standard error to the left. So I get beta hat j minus gamma standard error of beta hat j. So this is telling me 1/2 of the beta j is bigger than or equal to beta hat j minus the gamma times standard error of beta hat j. So this give me that inequality. And then if I do the other one, the other half, if I do this part, then you get the upper half of the inequality. So do it as an exercise. And then you can see that what we really showed is an interval, right? So the probability that beta j belongs to this interval, beta j minus gamma standard error of beta hat j, and beta hat j, the upper bound is plus gamma standard error beta hat j. This probably is 1 minus alpha. Okay, that's kind of my confidence interval. This is like an A hat that we had. This is B hat, and the whole thing is I hat. Okay, so we constructed a random interval that such that it contains the true parameter with probability 1 minus alpha. Okay, and oftentimes you just write it as this happens to be symmetric. So the center is beta hat j or point estimate, and it's symmetric around that. So you'd write it as beta j plus minus, this is gamma, times the standard error, which you probably have seen before. Okay, that's how you can drive it. So it would be an interval which contains, sorry, the center is beta hat j, our point estimate, and then you go gamma standard error above it, and then minus gamma standard error below it. And you get the interval. Okay, beta hat j minus this, beta hat j plus this. Okay, so it's a symmetric interval around beta hat j with length 2 gamma standard error of beta hat j. It's just that the scale multiple of the standard error is determined by alpha via the T distribution. And so you can see that the interval changes. So when you get more like an ensemble of samples, you get different beta hat j's. Each time beta hat j changes, a standard error is also a random quantity. That also changes with both the length of the interval and the center would change. But all you can say is that, okay, if I do it 100 times, look at all these intervals, like 95% of them on average would contain this requirement. Okay, does that make sense? Okay, I think I stopped here in the in the morning session. You can repeat it. Same process, the same statistic can be used to do the hypothesis testing problem. And you can actually invert this or the duality to use this to get the actual test, but we're gonna do it hopefully next time quickly. And then we move on to the same idea about the regression function. So you can also do confidence intervals and hypothesis tests about the regression functions and more later. Okay. Questions? Okay, thank you guys. See you on Thursday.
No.